This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide changed all that. It hit with the force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just a question of when. Thousand years.
Here's the question. So the question is,
The atmosphere,
every time there's an
creating a
impact,
suffocating blanket of dust the sun was powerless to penetrate for 1,000
and it's going to cause some kind of
years.
back wave traveling about 1,000 miles per hour. You got the fire, you got the heat, you got the destruction, you got the sound. Where do they all come from? All right, so that's what we're going to be. The only thing we know so far is the conservation of mechanical energy. Okay, it's a very limited case of reality, believe it or not, guys. It's a limited case of reality. In that sense, that imagine that this guy's in a relationship feeling really good, high, emotionally and physically high in this relationship. And then a breakup, she lets go. He's got all this energy, he's got potential energy. So what happens to the potential energy? Just before impact, it's going to turn kinetic. And then what happens upon impact? Kinetic energy goes away. So what happens to all that mechanical energy? So that's what we're investigating. Remember, Galilei ended up discovering the concept of inertia while he was investigating the free fall phenomena. And then he said, this ball, ignoring surface friction, is going to roll down and go back up the same height. So the question is why? So ignoring surface friction, the ball is going to keep going back up the same height. Okay, that wasn't the question. He was somewhat interested in, but he didn't know how to answer that question. I think we kind of know how to answer it today. Here's what happens. Ignoring surface friction, what's the only force acting? The only force acting is gravity, right? If gravity is the only force acting, what happens to mechanical energy? Mechanical energy remains constant. That's what happens to mechanical energy. So which means that the initial energy is going to be potential energy. And then when you let it go, under the influence of gravity, potential energy is going to turn into kinetic energy. And the kinetic energy is going to turn back into potential energy. All right, so when gravity is the only force acting, what happens? Potential energy gets converted into kinetic energy. Kinetic energy gets converted back into potential energy. So which means that mechanical energy is going to be conserved. All right, so that's the easy one. Okay, real life is a lot more complicated than that. So here's real life work.
Hoffman wanted to jump up to 30 feet. He couldn't build a ramp high enough, so he used a motorbike to tow him up to speed.
So this guy is using a motorbike. You notice he's getting a bit of height. I mean, he started at this point, and this guy just goes up all the way up to that point.
Hoffman wanted to jump up
so
to 30
motorbike
feet.
makes a big difference.
He couldn't build a ramp high.
So what does the motorbike do for him? Well, here's what the motorbike does. It uses a propulsive force. And you start off at this point, so this is your initial mechanical energy. And then you end up gaining mechanical energy. In fact, you end up getting quite a bit of mechanical energy. All right, so because of the propulsive force, what's happening is the mechanical energy changes, you end up gaining mechanical energy. So mechanical energy is gained. So the amount of energy that you gain, where do you get the energy from? Well, obviously, you're using a motorbike, guys. Where do you suppose the motorbike is getting its energy from? Of course, it's getting it from energy that you put into the gas tank, right? Okay, so what kind of energy do you put in the gas tank, in essence? Well, obviously, it's going to be chemical energy or chemical potential energy. That's what we're saying. So energy is going to be stored in the form of chemicals. All right, so that's otherwise known as fossil fuel. So which means that you can trace the energy back to its source. Original source of the energy is the dinosaurs. So the next question is, where did dinosaurs get their energy from? They got their energy eating other things, right? So they would be eating other dinosaurs. That's one way of getting it, or plant life. So the next question is, where does the plant life get its energy from? Plant life still gets the energy from the sun, right? So the plant life is going to get the energy from the sun. So which means that they will get from the sun. What do we get from the sun? We end up getting light from the sun. What else? We end up getting heat from the sun. Heat and light and chemical processes is what sustain life here on Earth, in essence. So the next question is, where does the sun get its energy from? The sun ends up getting its energy from a nuclear fusion. Its fusing is the hydrogen. Hydrogen fuses into helium. When hydrogen fuses into helium, you end up getting heat. You end up getting light. All right. Out of that, you can also generate electrical energy. So this little bit of mechanical energy that you gain It's the amount of energy that you're able to convert from either chemical, light, heat, or nuclear. That's where it comes from, in essence. So the gain mechanical energy is going to come from a conversion process of either chemical, light, heat, nuclear. Speaking of the sun, all right, what fuels the sun is the nuclear fusion, which means that the hydrogen is turning into helium, it's fusing into helium. So what does the sun get its hydrogen from? Just get the hydrogen. Sun originally gets the hydrogen from space, right? So next question is, where did space get its hydrogen from? You can trace this all the way back to Big Bang. All right, so the hydrogen is the first element which was created in the universe. All right, so this little bit of energy that you gain through the propulsive force, conversion of energy from other forms into mechanical energy, can be traced all the way back to Big Bang. If that's the case, why do we have to pay at the pump, guys? Why not just get into the car and drive away? Why not do it that way? What that means is the energy has got to be free, right? Because all energy could be traced back to Big Bang. All right, just try that approach. Just fill up the tank, leave. But when you're arrested, eventually you will be arrested, obviously. Make this argument with a tremendous amount of confidence to the judge to see what happens. All right, so energy is free. It's always been free. Believe it or not, you're never paying for the energy. You're paying for the service. All right, so it's obviously fossil fuel. Somebody had to dig it out. Somebody had to process it. Somebody had to transport it, make it available for you. So you pay for the services, in essence. The other thing that I want you to notice is, look, you end up gaining mechanical energy, right? This is the amount of mechanical energy that you gain. So mechanical energy is no longer constant. Okay, so what that means is the propulsive force is not a conservative force. Gravity is a conservative force, but not the propulsive force. So propulsive force is not a conservative force. Right. Galileo's original line experiment. When Galileo did this experiment, of course he immediately noticed that the bulb would not go back up the same height. Because that's the reason why he said, ignoring friction, the bulb will go back up the same height. If you're not ignoring friction, the bulb will never go back up the same height. It means that you will lose mechanical energy. So the final energy is going to be smaller than the initial mechanical energy. So some of the mechanical energy is going to be lost. So where does the lost energy go? Number one, it's going to generate sound. So sound is a form of energy. If you actually measure the temperature of the surfaces, you will notice that the temperature of the surface is going to go up, which means that the surface is going to heat up just a little bit. So lost energy is going to appear in the form of sound. It's going to appear in the form of heat. If there's just too much friction, what's going to happen is, all right, so if there's too much sound, if there's too much friction, so what's going to happen is the surface is going to heat up to an extent that it's going to glow, which is otherwise known as fire. So you end up getting fire out of it. So through friction, once again, what happens to mechanical energy lost energy is going to appear in the form of other types of energy. So which means that there's a conversion to other types of energies. All right, so this was a good learning experience. So even if mechanical energy is not conserved, the total energy still is. So if there's a propulsion system, know that the mechanical energy is no longer conserved, right? Which means that mechanical energy is going to be gained.
His favorite part of
gaining mechanical energy,
the job is testing the products. He doesn't pedal. He uses his upper body to pump himself up to 35 miles per hour, the speed he needs to get airborne.
It's great. Like when you look down on the ramps like that, you focus on the coping, which is that bar right on top. And once you stop focusing on that coping, you just see the whole ramp and the whole surroundings and stuff. So it just gives you such an awesome perspective. You just feel like you're just hanging up in the middle of the sky.
His favorite part of the job is testing the products. He doesn't pedal. He uses his upper body to pump himself up to 35 miles per hour, the speed he needs to get airborne.
It's great. Like when you look down on the ramps like that, you focus on the coping, which is that bar right on top. And once you stop focusing on that coping, you just see the whole ramp and the whole surroundings and stuff. So it just gives you such an awesome perspective. You just feel like you're just hanging up in the middle of the sky.
His favorite part of the job is testing the products. He doesn't pedal. He uses his upper body to pump himself up to 35 miles per hour, the speed he needs to get airborne.
It's great. Like when you look down on the ramps like that, you focus on the coping, which is that bar right on top. And once you stop focusing on that coping, you just see the whole ramp and the whole surroundings and stuff. So it just gives you such an awesome perspective. You just feel like you're just hanging up in the middle of the sky.
His
okay, Sarah, give yourself
favorite part
10 points for that nice little comment. You're absolutely right on that one. It's perfectly.
The job is testing the product.
Yes, it's exactly what a propulsion system does. Okay, so notice that in this case, this guy, despite the fact that he's not pedaling, right, he's still gaining energy because he's rocking his body back and forth. Okay, so which means that the propulsion force is being used, in essence. Okay, so the muscles generating propulsion force. So if it's a propulsive force that he's using because he's getting mechanical energy, what is the original form of energy that turns into mechanical energy? All right, so the muscles are getting their energy from what? In essence, the muscles are getting their energy from the food that you eat, right? So what kind of energy does the food have? It's chemical energy. It turns into heat. Or then there's a chemical process that turns into heat, and then that turns into your mechanical energy, right? So that's the same process. So the muscles generate this propulsive force. So that was another example of how you utilize a propulsive force. Living things usually utilize a propulsive force. So they have this chemical energy, the food that they eat, so that turns into heat, and then obviously it turns into mechanical energy, it turns into motion, kinetic energy, blah, blah, blah. And it goes on like that. And when there's friction present, so the mechanical energy is no longer conserved because you end up losing mechanical energy. So that's what happens. You end up losing mechanical energy. So lost energy is going to appear in the form of sound. So you get sound out of it. What else? You end up getting heat out of it. If there's way too much friction, surfaces will glow. You end up getting fire out of it. On top of that, obviously, things may start to disintegrate. So things will start to break apart. So that's what happens. One thing that we discovered from this is even if the mechanical energy is not conserved, total energy still is. So which means that the total energy in the universe must be constant. So energy cannot be created nor destroyed. So you cannot create energy. It's not the question. You cannot destroy energy. Energy only gets converted from one form to the next. All right, so this is known as the conservation of total energy. And this video is going to illustrate beautifully.
Sacramento, California. Engines roar and tires screech. The National Hot Rod Finals get underway. Veteran driver Hans Dussel rolls to the starting line. The green light and floors it. Then, disaster. Up in the stands, Honda's girlfriend, Kay Toplicar, watches in horror.
It just exploded in ball of flames. Everyone who had witnessed that accident was very concerned that Hans would be seriously injured, not dead.
Despite his 30 years of racing experience, Hans cannot avoid the terrifying crash. It is incredible that he survives.
I knew there wasn't much I could do with it except hold on. At that time, way before I hit the guardrail, I knew I was in trouble.
As Hans roars down the track, he suddenly loses control. He fights to steer clear of the rail, but he can't.
When I impacted that car at the guardrail, I was doing somewhere between 150 to 170 miles an hour.
Hans skids in a pool of oil left from an earlier mishap. As he accelerates, the rear tires spin out. His car smashes into the rail, flipping onto its side. Now he's caught in a fiery death trap. And there's no way out.
I saw sparks coming off in front of the car. I thought to myself, we're probably going to have a fire now. And then all of a sudden, you could hear the grinding of the car when it was sliding down the racetrack. The body was coming off in pieces.
The hot rod disintegrates and the fire burns itself out. Although Honda's in shock, amazingly, he is able to walk away from the wreck.
When I unbuckled myself, I basically kind of rolled out of the car because the car was sideways laying on the ground. When the paramedics came over, that's when I finally realized what I just went through.
His car is a total loss, but Hans is thankful to be alive.
As bad as this wreck was, by rights, I should have been hurt. I maybe should have been killed. So I was very, very fortunate.
Despite his 30 years of racing experience, Hans cannot avoid the terrifying crash. It is incredible that he survives.
I knew there wasn't much I could do with it except hold on. At that time,
Okay, so
I knew I was in trouble.
okay, so let's just get rid of this. Okay, the nice thing about this is you can see the conservation of energy completely. All right, so the first thing you do is turn on the ignition. You turn on the ignition. All right, so what happens? When the car is not moving, the engine is going to heat up. So chemical energy is going to turn to heat. The engine is going to roar. So it's going to turn into sound. The car is going to start to move. It's going to start to turn into kinetic energy. Then, obviously, the car is speeding up, turning kinetic energy, and then boom, impact starts. There's a lot of friction. So what does friction do? Tremendous amount of sound. Heat. And eventually, the surfaces start to glow. So you end up getting this fire. And eventually, what happens is the car is going to start to break apart. So what's happening is, I'm going to say the final form is going to be deformation. So the vehicle is going to start to deform. All right, so the race cars are built to break apart. You notice that there's no dent on this car. This car is not meant to crumple. All right, it's designed to actually break apart. The reason why it's designed to break apart is you want to take the energy away from the driver, right? Okay, I'm not muted, right? No, I'm not muted. You can hear me fine, right? Initially, I was talking to myself. Anyway, cool. Give yourself 5 points for noticing. All right, so there are two ways you can deform a car. One of them is you can let it crush, but if you do that way, the energy is going to stay inside the car. At extremely high speeds, you don't want that. You want the car to break apart so you can take the energy away from the driver. So what that means is the force that can harm the driver, the amount of force that can harm the driver, potentially harm the driver, you reduce that force by breaking the car apart. All right, so the final form, just think of it this way. Just pretend the final form is going to be deformation.
One little mistake, and you're in a lot of trouble.
The tires were squealing. The back tires were squealing.
I thought she locked up the brakes.
He told me to let up on it. He said to ease it back down, and when I did, the pedal hit the floor.
The Blazer just kept going faster and faster.
And Sean kept screaming at me, hit the brakes, hit the brakes. And there were none.
There was really nothing that anyone could do.
Turned around and told Sean that I loved him, and that was the end of it.
I will never ever forget the sound as it bounced on the rocks. You can hear metal hitting. You heard people screaming.
For some reason, one of the front brake seals blew out. When that happens, there's a safety that will automatically lock the fluid in the back brakes. But due to the steepness of the hill, the back brakes weren't able to hold.
The vehicle was moving so fast.
I could see the kids frantically trying to do everything that they could to stop the Blazer.
There was no way out. The only way out was straight down.
I thought I was going to die.
There was one spot of sand in that entire area, and that's exactly where they left it.
It's a hard memory. It's a very hard memory.
Okay, this one is kind of weird. Number one, what is it that they're doing up there? Obviously, it's not part of the road. They're up there because they know that they can be up there because they got the right type of vehicle as far as they're concerned. It allows them to be able to get up there and come back down there. Right? You could never do something this stupid. Using
The tires were
so for the obvious reasons, brakes don't work.
I thought she locked up the
the back tires were
right, so without brakes, what's happening is gravity takes over. Gravity tries to turn that potential energy into kinetic energy. There's also friction acting, so there's going to be heat, there's going to be sound. The final form is going to be deformation, obviously. So that's deforming. And
there was no way out.
Is the couple
The only way out
deforming and the
was straight down.
Porsche starts going to get deformed. So things okay. One of the weirdest things about this movie is this is almost like the biggest movie.
I thought I was going to die.
This guy. Originally, there's one single camera angle. This guy sees what's happening. Okay, he goes and grabs the camera, turns it on.
There was one.
Okay, this is kind of weird in a disturbing sort of way. Because this guy is either a friend, a family member, or a relative, and you know he's about to capture somebody's demise. Why would you want to do that?
Entire
Guessing it's
area, and that's exactly what.
this is weird. This is kind of weird. All right, so this brings us to the next point. Asteroid impact.
Have you ever wondered why is the sky blue?
You get fired.
And why do flesh-eating meteorites rip through our universe? This ad exposes the God's honest truth.
That fire and destruction. That fire and destruction. All right, so let me ask you. Name of this movie is Deep Impact. It came out in late 1990s. I think it's 98 or 99. It came out about the same time as Armageddon did. Except Armageddon did really well. This movie not so much, because the storyline was really weak. This guy, the director, he ended up going absolutely apeshit. Special effects. So that's what we're going to focus on, the special effects. Right, so it's Deep Impact. So you got the asteroid just hitting the ocean. Then immediately you will see the fireball. You end up getting the fireball. Creates the shockwave. The shockwave is going to be traveling about 1,000 miles per hour. It's going to create a tsunami. This tsunami is going to start to flood all these continents. And that becomes the premise of this movie. Okay, so it creates a tsunami and so forth. Okay, so here's a question for you. An asteroid impacts, you end up getting heat, light, sound, formation. So what is the original form of energy? Obviously, it's the kinetic energy of this, but don't forget it's also got potential energy, right? It's also going to have potential energy. All right, so the initial form of energy is going to be mechanical energy. Having said that, okay, so it's between A and C. Okay, it's one person picked B. I think the best answer is going to be C. So you guys get the one. Okay, so the initial form of energy is going to be mechanical energy.
The principles of a trampoline are very basic. Up, down, up, through. The principles of a trampoline are...
Okay, so going back to this one, interesting thing is, you know, this is gravity, right? Gravity takes over. So this guy has gravitational potential energy. Then what happens to gravitational potential energy? It turns to kinetic right at this point. So when he hits the mat, it's going to stretch the mat. So which means that he deforms the mat. Mat has something called the restoring force. So which means that you do work against the restoring force. When you do that, you end up storing energy in the mat. So restoring force, just like gravity, it's going to be a conservative force. So which means that the mat is going to become energized. So it's going to have deformation potential energy or elastic potential energy. So you deform the mat, it has elastic potential energy. So mat transfers the energy back to you. At this point, you got kinetic energy. And then you end up going up against gravity. Now you got gravitational potential energy. So what happens is the gravitational potential energy turns into kinetic energy right at this point. And then you push against the mat, you deform it, turns into deformation potential energy or elastic potential energy of the mat. And then you take the energy back. At this point, you got kinetic energy, and then boom, it turns to potential energy. Right? So you got two conservative forces acting on you. Gravity is a conservative force, and restoring force is a conservative force. Okay, by doing work against these conservative forces, you end up storing energy in the object that you're lifting in this case. Or by deforming the surface, you end up storing energy in the mat. And that energy gets transferred to the person in essence. Right? So that's what's happening.
I want to tell you some important news that every parent needs to hear, although your kids may not want you to. Just this week, the Consumer Product Safety Commission reported that injuries from trampolines have nearly tripled over the past decade, and most of the victims have been children. Still, trampolines are a hot backyard item, and they look like so much fun. But how safe are they? Arnold Diaz has a warning you shouldn't miss, because if your children don't have a trampoline, someone they know does.
Today, for the first time ever, trampolining premieres as an Olympic event. World-class trampolinists like 19-year-old Californian Jennifer Perilla, seen here practicing, spring 20 feet into the air to perform spectacular stunts. But there's another picture of trampolining that's not so pretty. This home video shows what's happening more and more on backyard trampolines around the country. Kids getting injured. Watch as Russ Johnson loses his balance and breaks his ankle.
Oh, my parent!
4 million backyard trampolines have been sold in the past decade, and many believe sales will skyrocket after the Olympics. But listen to the answers we got from professionals like national trampoline coach Judy Wills-Klein when we asked if they would buy a backyard trampoline.
No, I would never have a backyard trampoline, personally.
We got the same surprising answer from Olympic hopeful Jennifer Perilla.
If I had kids, I would not allow them to have a trampoline in the backyard. I would send them to a coach.
Trampoline safety expert Mark Rabinoff goes even further. He's testified against the industry in a number of injury cases.
Backyard trampolines are extremely dangerous. I wouldn't buy them. You don't find them in gym schools. You don't find them in schools anywhere else. You won't find them in Olympic competition.
As sales of backyard trampolines have increased, so have injuries. Sometimes people fall off and get hurt, but studies show most are injured on the trampoline, landing the wrong way, or colliding with another jumper, getting tangled into springs, or hitting the frame. Almost 100,000 people went to hospital emergency rooms last year from backyard trampoline injuries, and now a leading medical group has come out strongly against their use.
If a parent asks me my opinion about trampolines, I simply don't buy one. If you have one in your backyard, get rid of it.
Dr. Gary Smith, director of the Center for Injury Research at Children's Hospital in Columbus, Ohio, has done a study of trampoline injuries. Half the injuries are strains and sprains, but a third are fractures.
We've seen children come in with broken bones that were just devastating injuries. We've had what we call compound fractures. The bone actually comes out of the skin. We've seen elbows that have been shattered.
In just one day this spring, his hospital treated 3 separate trampoline injuries. 5-year-old Allison Anderson fractured her elbow. 10-year-old Forrest Woolham broke his wrist. And 11-year-old Brittany Delgado fractured her ankle. There have been so many injuries, the American Academy of Pediatrics now recommends that pediatricians should advise parents never to purchase a home trampoline or allow children to use home trampolines. But Lanny Lokendahl, the director of the Trampoline Manufacturers Association, says they're safe.
It's very easy to use it safely if you adhere to the safety instructions that the manufacturers discuss in their user manual.
The problem is people often don't follow the rules, despite the fact that there are warnings on the box, in the manual, even on the trampoline itself. One of the most important rules, only one person at a time, is clearly stated. But drive around any neighborhood and you're likely to see what we did. Here in Mattawan, New Jersey, between the Gregory kids and their friends, we found up to 6 jumpers at a time. The kids don't like to jump one at a time, says Dawn Gregory.
Just to have one on there, they're bored. So, we upped it to 2, and now we've upped it to depending on who's here.
But studies show a majority of injuries happen when there's more than one jumper. The reason became obvious when I got on the trampoline and tried jumping, having never been on one before.
Now imagine if somebody else came on like me. Oh. Scary, isn't it?
Right, I think you lose your balance right away.
Absolutely, you lose your balance instantly.
As you can see, multiple jumping can put just broken children of different variety of injuries.
Okay, everything else is kind of common sense.
Happen when there's more than one jumper.
And kids just flying into each other and all that stuff, and you losing
the
your
reason.
Okay, commonsensical stuff is the stuff that I don't care. All right.
Became obvious when I got on the trampoline and tried jumping.
Hidden aspect of it, when somebody's jumping,
having never been
you end up storing energy
on one before.
All right, so which means that there's enough force in the mat, stored force in the mat.
Now imagine
that can propel you enough.
Somebody else came on like me.
Oh. So the guy loses
balance. Scary, isn't it?
Right, you lose your balance right away.
Absolutely, you lose your balance instantly.
As you can see, multiple jumping can cause kids to stumble and fall and to be launched into each other. And if a child coming down,
so
children of different weight on one before.
Now imagine.
Yeah, let me just make this. All right, so let's just, so I can talk. The one that I'm interested in is what happens when multiple people are jumping up and down. All right, so the mat is going to become energized at all times, which means that it's going to have enough stored force in it. When we say stored energy, we mean enough stored force can cause motion. That's what it is. Got multiple people jumping up and down. So which means that at any given point in time, it's going to have enough force stored in the mat that can cause motion. For the most part, it's harmless. Right? So more energy that you can store in it, more force is going to be able to generate. So which means that higher up you will go. Right? And that makes it fun. Okay, the worst case scenario is what you just saw here, but we can illustrate it better. Okay, so just listen to it first, and then we'll just jump back.
Powerful rebound effect is apparently what happened when Russ Johnson was jumping with two friends.
All right, so you just saw that. So what happened is his ankle
Broken, Chris, I can tell.
His ankle wasn't just broken, it splintered into 36
literally splintered.
pieces. Two large metal screws had to be surgically implanted by orthopedist Dr. David Muron.
This type of injury pattern would be equivalent to a fall, for instance, from a 10 or 20-foot height directly onto a hard surface.
2 years later, Russ says he's in daily pain and still can't run or jump.
Okay, so let's watch this. While you're watching, let me explain the physics of it. This is something weird happens. All right, so a number of people are jumping up and down. Mat is going to be energized, which means that it's always going to have enough force stored in it that could cause motion. Obviously, there are a couple of ways you can cause motion. Number one, you can just propel someone in the opposite direction if the body is going to be able to handle that kind of force. If the person ends up rolling an ankle, obviously it's going to end up causing formation. So it's going to appear in the form of deformation, which means that the ankle is going to explode in this case. Now, you got 3 people jumping up and down. So which means that this mat is at all times it's energized, which means that it's got enough force stored in it that can actually propel any one person up to 4 feet, 5 feet, or 6 feet. And the energy gets transferred between each and every single kid. And this kid goes up like 4 feet, so is this kid. It's at all times it's energized, and this kid just decides to jump on one single foot. And then when he does that, he rolls the ankle. Remember, it's got enough energy that can propel you in the upward direction. Likewise, the body's not able to get the propel in the upward direction, so it's enough energy to break your bones. So that's what happens in essence. It's kind of analogous to the other guy said, like someone jumping onto your ankle from 10 to 20 feet above. It's more like 6 to 7 feet. It's still large enough to break your ankle, obviously. All right, so that's the hidden damage. That's the hidden problem of what can happen.
June 20th, 1999, Santa Barbara, California. Stacy is among 10 top female pole vaulters competing at the 4th annual Beach Pole Vault Challenge. In this big buck showdown, any contestant that jumps higher than 15 feet gets a whopping $100,000. No woman has ever cleared this towering height on U.S. soil. With only one jump left, Stacy clears 14 feet 6 inches and wins the competition. But she is still 6 inches shy of $100,000 and a new woman's pole vaulting record. The bar is lifted and set at 15 feet and 3/4 inches. Stacy has 3 chances to set a record and claim the cash. But she comes up short on her first 2 tries.
And on my last attempt at the record height, I said, you know, I got to give it my all right here. I got to put a really good vault together.
On her last try, Stacy clears the bar and vaults into the record books.
It was the greatest feeling going over the bar and coming down and landing on the mat.
All right, so here's a question for you guys. How fast does she have to run in order to clear this height? Okay, so how fast does she have to run in order to clear this height? All right, let's take a look at that problem. How fast does she have to run? Okay, so this is problem number 11. She's clearing like a bar which is at 15 feet above the ground. So the speed she has is going to go into bending the pole. So it's going to turn into deformation potential energy of the pole, because the pole has that restoring force. So you can actually transfer the energy to the pole, and then she takes the energy from the pole, so it turns into gravitational potential energy, right? So how fast does she have to run in order to actually clear this height? So initial height, I'm going to take that to be 0. Final height is going to be where the bar is set, give and take 15 feet. I'll assume that gravity is doing force acting. All right, so I got the height at that point. Initial energy is going to be all kinetic, and then you got the deformation potential turning into gravitational potential energy. So the final height is going to be gravitational potential energy. So the final energy is going to be gravitational potential energy. Initial is kinetic energy. The final is going to be gravitational potential energy.
Are we assuming she goes straight up?
All right, so here's the kinetic energy. Here's the potential energy. Stop where I am.
Wait.
So we are solving for M. Let's solving it for VO. Okay, so
Wait.
we're putting an expression for that.
So we are assuming she's going straight up. We don't have to worry
this
about.
This is going to give us roughly about 21.5 miles per hour. Okay, so the question is, was she running at 21.5 miles per hour? All right, so, okay, so do you think she was running at 21.5 miles per hour? You can do it. She's obviously going. The question is it possible for her to run that fast? So that question is, no, really. Why not? Because these guys
go without
run
machine
23 miles per hour.
His average per hour makes him faster than even the
130 seconds. This guy was going a little bit over 20. It was going a little bit over 23 miles per hour at the time. Right? He was going over 23 miles per hour. Okay, so Sarah, give yourself 5 points. Okay, so there's some assumptions involved, and like I always say, stuff is as good as the assumptions that you're making, right? So we got some assumptions. We got some assumptions involved here. All right, so the question is, what are those assumptions that we're making, which are not realistic? All right, this number one, I took initial height to be 0. In reality, the initial height should be her center of mass. Okay, her center of mass is located here. Also, assume that kinetic energy gets converted into potential energy, and potential energy turns into the gravitational potential energy. So we got some assumptions, which may or may not be accurate. All right, realistically, though, the extra energy is not coming from her speed; it's coming from her body. Right? She's got ample energy.
Thank you.
She's using her muscles and all that stuff. The extra energy is coming from her muscles. Okay, it's not just from the speed, most of the muscles that she's utilizing. She's strong. She's muscular. Everything is extremely well timed, so things work out.
The referee says take the strain, and what a strain
Right,
it's going to be.
so this one,
Those floating blocks again hammered into the ground. That gives the
question is, what's power?
competitors a firm grip.
What is power?
It's almost like a rowing action, and good rhythm.
Okay, so the question is, which guy
Setting
is
up
more
a rhythm,
powerful?
and that's what he
Okay, I ask you that question. You guys kind of know the answer immediately. Okay, it's not a complicated question to answer.
needs to go for a good time.
Okay, so the first guy pulls the same airplane.
Coming up to 30 seconds.
It
certainly is going to be very fast. 34.34. That has to be the winning
Second guy
performance. The
is
clock will
gonna
stop any
pull the same
moment.
airplane. So for him, it's going to take 42 seconds. All right, so if that's the case, which guy is more powerful? Or the first guy is more powerful, right? Because both of them do the same amount of work. All right, so both of them. So assuming that she went straight. Okay, so both of them are going to do the same amount of work, except the first guy does it much faster. So which makes it much more powerful.
Now 42.
So power is how fast the work is done, how fast the energy is transferred, how fast the energy gets converted. All right, so that's the meaning of power. How fast the work is done, how fast the energy is transferred, how fast energy is converted. Okay, it's expressed in terms of horsepower in the United States. Physics is going to be expressed in terms of watts.